All right, so what I'd like to do today is work through some things. I'd like to work through a long nonlinear bifurcation problem that I've given on past exams for pure differential equations classes. And while we work on it, we can talk about some other ideas you hear about in the lectures and with this extra reading, including possibly talking about trapping regions, for example. And then also briefly talk about Hamiltonian systems and gradient systems, which are in this last lecture. You should watch lecture 32 before the exam. And if it's on the in-class portion, I would just test you on the basics. If it's on the take-home portion, it might be a little bit more involved. But pretty much any way you do it, you got to use technology. And then the last main thing to do today is just, as far as the linear algebra goes, is kind of like trying to review the main facts to know and main calculations to be able to do without necessarily getting into details on an example. Well, let's look at an example here. So this is an example I've given on some old final exams for a plain differential equations class. You can see we've got a nonlinear system here that involves a parameter A. So it's a one parameter family of nonlinear systems. We're going to be thinking about equilibrium points and linearizing with the Jacobian matrix. And we should also talk about, I think, be worth doing to talk about whether the equilibrium points are hyperbolic or not, whether this Hartman-Grobman theorem applies or not, that kind of thing as we go. Let's go ahead and write down the system. Get it in my memory here. Okay, I think I got it. So it's dx dt equals, oh boy, I think I've forgotten that already. The y minus x, y minus a times x plus x cubed. The other one's y minus x. Y minus ax plus x cubed. dy dt is y minus x. So you can see the right-hand side of the dx dt equation does depend on the parameter a. I could call this f sub a of xy to emphasize its dependence on the parameter a. The dy dt equation right-hand side does not depend on a. I could just call that g of xy. One thing that's nice about this particular system, even though it's nonlinear, is that if I set both right-hand sides equal to 0, I can solve for the noclines as functions of x. I can easily solve for y as functions of x. If I set this equal to 0, the x nocline solve this equaling 0 for y gives y to be ax minus x cubed, right? I'd have to subtract, or I'd have to add ax to both sides and subtract x cubed. So that tells me if I can graph this function as a function of x for different a's, that tells me what that x nocline looks like. And the y nocline is pretty easy. The y nocline is constant. It does not depend on a. It's the line y equals x. So that's the first thing I do, is I find the noclines. And I might ask you to do that. Where the distinct noclines intersect is where you get equilibrium points. So once again, it's fairly easy here because just set these two things equal to each other and solve for x, and that gives you the x coordinates of the equilibrium points. And then use the second one to find the corresponding y coordinates, and it's pretty simple. Y equals x. Well, at any equilibrium point, y equals x. The equilibrium points have to be in the line y equals x. But to solve for them, again, set these things equal to each other. Ax minus x cubed equals x. That's equivalent if I, for example, add x cubed to both sides and subtract ax from both sides. I could write it like this. I added x cubed to both sides and I subtracted ax, and then factor out an x and then switch sides. And it's always good to factor if you can. You can factor a common factor of x out. And get that. Which definitely gives x equals 0 as an x coordinate of one equilibrium point. And if x squared plus 1 minus a equals 0, that means x squared equals a minus 1. Other equilibrium points are going to have x coordinates plus or minus square root of a minus 1. You don't have to use the quadratic formula here. Another nice thing. Does that make sense? I'm imagining setting this equal to 0, subtracting 1, adding a to both sides, and taking the plus or minus square root. But because it does involve a square root, it's not always going to be a real quantity here. And we are after real equilibrium points, not complex equilibrium points. Eigenvalues can be complex and are useful to think about that way. But equilibrium points, we want real equilibrium points. So this is only going to be real when a is greater than or equal to 1. A equals 1 must be a bifurcation point, where we go from having one equilibrium point to having, well, once a is bigger than 1, to having 3. Write down those cases. When a is less than 1, in that case, a minus 1 is going to be negative. We get just one real equilibrium point, which is all we care about is real ones, at 0, 0. And that's actually true even if a equals 1. So I can write a is less than or equal to 1, because if a equals 1, that becomes a 0 still. If a is bigger than 1, then we get 3 equilibrium points. 0, 0, square root of a minus 1, comma, square root of a minus 1, and negative square root of a minus 1, comma, negative square root of a minus 1, right? Because, again, at any equilibrium point, the x and y coordinates have to be the same. So I found x coordinates, the y coordinates have to be the same. I do not want to mix the pluses and the minuses up here. I would now want to say, for example, that a point with coordinates square root of a minus 1 and negative square root of a minus 1 is an equilibrium point. That's not the case because the coordinates have to be the same. Okay, continuing to go here, just purely symbolically without bothering to try to make a phase portrait yet. We've learned that linearization is useful. Jacobian matrix. Actually, at the origin, we can linearize just by throwing away nonlinear terms, just by ignoring that x cubed. However, even at the origin, it doesn't hurt to use the Jacobian matrix. So the Jacobian matrix, J, will in general depend on A, the parameter, and you always plug points into it. And for a two-dimensional nonlinear system, it's a 2x2 matrix whose first row consists of partial derivatives of the first right-hand side function with respect to both variables, and whose second row is partial derivatives of the second right-hand side function, the g function, with respect to both variables. And those things are functions of x and y in general, and so that's why this matrix is a function. A function whose inputs are points and outputs are matrices. It's okay. Yeah, that's the general idea of a function, just takes inputs and gives you outputs. The inputs can be points and the outputs can be matrices. Partial of f with respect to x, treat the y as constant and the a as constant for sure. Differentiate with respect to x, it gives you 0 there, minus a there, and plus 3x squared there. 3x squared minus a. Partial with respect to y, treat the x as constant. You get 1. Right? Now go to the g function. Its partial with respect to x is -1. Its partial with respect to y is +1. There is your Jacobian matrix. Turns out to not depend on y in this example, but it could have. You always evaluate the Jacobian matrix at equilibrium points. Not that you can't evaluate it somewhere else, but it's just not as useful. So at the origin, which is always an equilibrium point no matter what A is, what we get when we plug in x equals 0, we get a -a up there, 1, -1, 1. Probably it's useful to think about the trace and determinant. The trace is going to be 1 minus a, and determinant will be -a plus 1 is also 1 minus a. Quickly think about the trace determinant plane. I hope you feel like you've gotten enough practice that with the trace determinant plane now that you could pretty quickly think about this. T and D are always on the same here. They're both 1 minus a. Graph T comma D as a function of a. It's a parametric curve where T and D are always the same. It's going to be on the line with a slope of 1 to the origin. And as a increases, these decrease. You got to be moving this way along that line. It's not a solution of the differential equation. We're not talking about a straight line solution then. This is not the phase plane. It's just a different plane, a TD plane, trace determinant plane. It's just a way of visualizing what's probably going to happen. What are the critical loci? The t-axis, positive d-axis, and the repeated root parabola. It's when you cross those critical loci that bifurcations occur, even not just in the number of equilibrium points, but also in the nature of the equilibrium point, in this case at the origin. When the values of t and d are such that you are over here, when a is such that you're over there, that's where the origin is a real source. Bifurcation occurs when you cross that parabola and you get to a real a spiral source. Bifurcation occurs when you cross through the origin, you get down to a saddle point. I'm remembering in my memory what these different regions correspond to. Saddle points down here when the determinant is negative. Real source over here when determinant is positive and you are under the repeated root parabola. Spiral source in here, spiral sink in here, real sink over here. That's from my memory. And if you want to do these problems quickly enough, it's good to have them in your memory too. When am I going to go through the origin? When t and d are 0. A equals 1. I'm going to go through the origin. And that corresponds to the value of a when we switch from 1 equilibrium point to 3. A equals 1 for sure is a bifurcation value. Is there another one when we cross the repeated root parabola? Yeah, I could try to figure it out. Again, the equation of the repeated root parabola is d equals t squared over 4, which is the same as 4d equals t squared. So I could figure out 4d here. That's 4 times 1 minus a is 4 minus 4a. And I could also figure out t squared. 1 minus a squared is 1 minus 2a plus a squared. Set these things equal to each other. That's when you cross the repeated root parabola. So we get a quadratic equation. And I'm not feeling good about something here. Oh, no, okay, I was just messing myself up. Ultimately, we can use the quadratic formula to figure out that other value of a. One of them is going to be a equals 1. Yeah. I subtract, no, excuse me, that's wrong. add 4a to both sides, and subtract 4. And that can be factored as a plus 1 times, no, a plus 3 times a minus 1, emphasizing that a equals 1 again as a bifurcation value. But the other one looks to be -3. So it looks like we cross here when a is -3, and you cross the origin there when a is 0, or 1, excuse me. What about the Jacobian matrix at the other equilibrium points? These two. Plug them in there. In both cases, we're squaring them, squaring the x coordinate. And because of that, you're going to get the same thing, no matter which point you plug in. J sub a at this equilibrium point is going to be the same as J sub a at the other equilibrium point. That didn't have to happen, but it did here. I'm replacing x with either plus or minus square root of a minus 1. That means the square root goes away, and the negative sign goes away with this one. So I get 3 times a minus 1 minus a. I still have a 1, a negative 1, and a 1. And that simplifies to 2a minus 3, 1, negative 1, 1. And that's got a trace of 2a minus 2 and a determinant of 2a minus 3 minus negative 1 is also 2a minus 2. Okay, so this example is working out nice. In both cases, the trace and determinant are the same. In this case, you're crossing in the trace determinant plane here. You're still on the line to the origin with a slope of 1, but now you're going rightward as a increases because these things increase as a increases. And once again, you cross the repeated root parabola when a equals 1 here. And actually, that's telling me when a is less than 1, I really shouldn't even be drawing this because it doesn't exist. Because the equilibrium points themselves don't exist as real numbers. So I should only think about this part over here. And I could once again figure out where it crosses there, what value of a. By once again doing the same kind of thing as I did before. Can I do that quick in my head here? No, probably not in my head, but 4d is going to be 4 times this will be 8. It's 4d here. 8a minus 8, and that's got to equal t squared. Square this, you get 4 times a minus 1 squared, which expands to 4a squared minus 8a plus 4. Subtract 8a from both sides. Add 8 to both sides. It looks like we get this, which can be simplified to this, which does factors a minus 1 times a minus 3. Now I'm going kind of fast here. Looks like we're there when a is 3. Lots of calculations here. What does it all mean? When I was talking about like the origin here, I was sort of implicitly using the Hartman-Grobman theorem without really saying it. Hartman-Grobman theorem is a more official way to think about linearization. Our textbook thinks about linearization very intuitively, which is fine. Saying, okay, find the Jacobian matrix, plug in the equilibrium point, and try to classify the equilibrium point. They do mention that it doesn't always work. When does it fail? It can fail when your eigenvalues are 0, when the determinant is 0, when you cross the trace axis. It can also fail, technically speaking, when you cross the positive d-axis, when you have centers with purely imaginary eigenvalues. It doesn't fail actually when you cross the repeated root parabola. This linearization with the Hartman-Grobman theorem, it doesn't fail then. can still use the Jacobian matrix to classify what's going to happen with the nonlinear system. So with the origin, we got a spiral, or excuse me, a real source when a is less than -3. I'm not going to write this down, but just say it. When a is between -3 and 1, we've got a spiral source. And when a is bigger than 1, we got a saddle point at the origin. With these 2 points, their Jacobian matrix is the same, so their classification is the same. It's a real source, a spiral source at first, and then it changes to a real source once we get past 3. In the directions on this problem on the test, I do have them draw a phase portrait, but not for every value of a. And I made it extra credit. It was a final exam problem, so not that this would necessarily be an extra credit part on yours, but it could be. I say to draw when a is 2. A equals 2, you are going to have 3 equilibrium points. The origin is going to be a saddle point, and the other 2 points are going to be spiral sources. Let's try to go ahead and do that. Draw it when a is 2. The system becomes dx dt equals y minus 2x, a is 2, plus x cubed. And dy dt is y minus x. Once again, the x node line is y equals ax minus x cubed, so that's going to be 2x minus x cubed. And the y node line is still y equals x. So now I'm just trying to draw a phase portrait as quickly as I can. And this, in the end, is always the hardest thing for people, is drawing these phase portraits. And again, I'm not looking for perfection. You can use StreamPlot to help, but you really should work at drawing them decently by hand. Not looking for perfection, but I'm looking for decent. The y node line is y equals x. You got to cross that horizontally because that's where dy dt is 0. Make horizontal line segments. Is it leftward or rightward? That depends. The x node line, which you're going to cross vertically, is the graph of that equation. Use your calculator or Mathematica to try to draw it accurately. I'm not going to bother with the scale here. The graph does look something about like this. It's a cubic. And it is an odd function. It's got origin symmetry. It looks something about like this. Cross that vertically. Equilibrium points when a is 2, remember those, there were plus or minus square root of a minus 1. So if a is 2, 2 minus 1 is 1. Equilibrium points here are 0, 0, 1, 1, and -1, -1. From the Jacobian matrix, I said a few minutes ago, this one's going to be a saddle point, and these two are going to be spiral sources. But let's try to see if we can write down about, make a drawing of what they look like here. Okay, listen carefully. So dx dt is this. It's going to be positive exactly when y is bigger than 2x minus x cubed, meaning you're above this cubic. That's where dx dt is positive. So any place time you're above the cubic, it's going to be rightward motion for solution curves, including in this little wedge here, because you're above the cubic. And dx dt is negative when you're below the cubic. And here, it's going to be leftward motion, including in this little wedge right in here, because you're still below the cubic there. dy dt is this. That's positive exactly when y is bigger than x and negative when y is less than x. In other words, dy dt is positive above the line to the origin and negative when you're below that line. Oops, it's above it over there. That gives you a place to be now where you can try to start drawing this inaccurately. Something's inaccurate though. This should be right order. So for example, if you start with an initial condition, say here, you got to go to the southeast. Will you cross the cubic? Probably. Certainly, if you start close enough to that equilibrium point, you'll cross the cubic. Will you go off this direction? Probably. Will you cross that line? Probably, at some point. And continuing to draw these solutions and crossing null lines appropriately. You know, this is far from perfect. What's good about it? One thing that's good about it is I'm crossing null lines correctly, or trying to at least decently. I should probably also add more solutions close to the equilibrium points to, for example, emphasize this is a spiral source in here. For example, draw arrows, and this one's a spiral source. You're sort of forced, you're almost forced to go away from them if you do this carefully enough. Now remember, the origin is a saddle point. Now you could try to find the eigenvectors for the Jacobian matrix to approximate the direction of almost straight line solutions. And what you would find is you're going to have one coming in approximately like this, one coming in over here approximately like this. And you'll also have, so those are going toward the origin, separatrices that are going toward the origin. You also have ones that are going away, and they have, if you think about it carefully, they have to go away like about like this. Emphasizing the origin as a saddle point. And solutions that go near the origin have this kind of behavior. So that's certainly far from perfect, but it's decent enough to, you know, give myself full credit if I was grading myself. Or close to full credit. I can nitpick about things, but it's not too bad. But this is what people have the hardest time with, right? It's hard to get that right without the technology. But I think it's fun and artistic, and I could try to spend more time and be even more artistic. But that takes time. This problem doesn't seem to have any applications. However, in the lectures to watch tonight or tomorrow, there are some applications that are emphasized for nonlinear systems to what are called Hamiltonian and gradient systems. And the Hamiltonian systems especially come up in physics a lot. In any situation where you've got friction, which is not really most situations, but we hope it can approximate many situations when the amount of friction is low. In such situations, you have what's called a Hamiltonian function. What's a Hamiltonian function? It's a function of two variables. Call it h in honor of Hamilton. in many real life models, H represents the total energy, kinetic plus potential. One model that's discussed is, well, a mass on a spring with no friction. Another model is a pendulum with no friction. You can create Hamiltonian functions representing total energy in those situations. And physically speaking, the derivative of the Hamiltonian function along any solution curve must be zero because total energy doesn't change, energy is conserved. Now that technically applies even when you've got friction, right? But some of that energy is converted to heat in that case. As far as the math goes, the Hamiltonian systems with this Hamiltonian function only occur when you have no friction. Now I can make up pretty much any function I want here. Maybe x cubed plus x times y squared minus y or something as my Hamiltonian function. That would not mean it's got any applications, but it is a Hamiltonian function that I can create a Hamiltonian system from. And what is that Hamiltonian system? It's a system where dx dt is the partial derivative of the Hamiltonian function with respect to the second variable y, and dy dt is the opposite of the partial derivative of the Hamiltonian function with respect to the first variable x. Kind of a weird thing. Certainly, if you've got some function h that's a function of x and y, you can do this. You can take those partial derivatives and you can plug them in there. What did they give us in this case? Partial derivative with respect to y here, treat the x as constant, is 2xy minus 1. You see that? Treat the x as constant, differentiate with respect to y. 2xy minus 1 and the opposite of the partial derivative with respect to x. Well, what's the partial derivative with respect to x? It's 3x squared plus y squared, right? Differentiate that with respect to x, treat the y as constant. 3x squared plus y squared, and I need to negate that. This may not be the greatest example. I think this example is not going to have any equilibrium points, which is why it's not the greatest example. Maybe I should make a little change. Let's make it a bit more interesting. Let's make this a plus sign here. So then this becomes well, that didn't help actually. Sorry. I'll go back to a minus sign here and make this a minus sign. That's going to change these partial derivatives. We've got a minus sign here. And also a minus sign here, making this a plus sign. Okay, that'll make it a little bit more interesting. Well, I should get some equilibrium points now. Without going into details about why, that's in the lecture and also in the reading. If I create what are called level curves of this Hamiltonian function, h of xy is x cubed minus xy squared minus y. Where'd my cursor go? There it is. There's the h. if I draw graphs of level curves of this, what are level curves? Well, if you've had or are in multivariable calculus right now, you know, it's where this function's constant. Curves in the xy plane where the function takes on constant values. If you haven't had multivariable calculus, I'm telling you what they are now. Drawing such curves is typically very difficult. And you almost always need some sort of technology. In Mathematica, you can do it with ContourPlot. Like this. And usually I like to add more of them, so I add an option, contours arrow, say 50 or something. These are curves in the plane along which this function h is constant. So for example, along this curve, and if the number is big enough for you to see that says negative 4.9 there. Along this curve, the outputs of the function are negative 4.9 at any point along this curve. At any point along this curve, the outputs are negative 9.8. At any point along this curve, the outputs are positive 9.8. Positive 14.7, positive 19.6. The corresponding Hamiltonian system of differential equations turns out is going to have solution curves which are on top of those level curves. So if I make a stream plot, I show this with a stream plot of the vector field negative 2xy minus 1 for the first component, and this thing for the second component, negative 2x times y minus 1, and negative 3x squared plus y squared. I should see, if I have not made a mistake, solutions that lie on top of those curves. Yep. And what this means is, it gives us another way to draw the phase portrait. We can get the technology to draw the level curves for us, and then we've got the solutions. Now, of course, I could always just resort to the technology and just do a stream plot without knowing about the level curves. But it does emphasize the meaning of the Hamiltonian system to know that that's true, and also emphasize how that means the Hamiltonian function, which could be total energy, is conserved. Along any solution curve, say like this one, the value of h doesn't change because you stay on the level curve. The total energy of the system doesn't change. Kinetic plus potential, if there were an application for this particular example. And that can be a useful thing. You know from physics, conservation of energy can be a very useful thing. It can help you solve problems. It can help you figure out like the motion of a pendulum, for example, if you know the total energy is conserved. Also with any function, including a function that I could call h still, you can create another system. This is a Hamiltonian system here. You can also create a corresponding gradient system, where gradient does refer to gradient vector if you're in multivariable calculus. It's a system where, once again, dx dt and dy dt are determined by partial derivatives of the function. However, they're different. Now, dx dt is the partial of h, not with respect to y, but with respect to x. And dy dt is the partial of h with respect to y, but no negative sign. So for this example, this one down here is going to be negative 2xy minus 1. And this one up here is going to be what I got here without the minus sign. So it's going to be positive 3x squared minus y squared. the level curves of H still tell you useful information for the gradient system. Whereas for the Hamiltonian system, the solutions are on top of the level curves. For the gradient system, the solutions are perpendicular to them. Orthogonal, normal. So if I also do a stream plot, say with red solution curves instead of blue, and make this the second component of the vector field, and make this one with the signs changed to be the first component. These red curves are perpendicular to all the blue curves. Every time they cross one of the blue ones, they cross perpendicularly. These systems are related to each other. In fact, if you wanted to think about orthogonality in dot products, the dot product of this vector field with this one is going to be 0. Because you get the product of these two partial derivatives plus the product of those two, and the minus sign there would make the sum of them equal to 0. The dot product of these two vector fields, no matter what point you're at, is 0. That's why the solutions in blue and red have to cross each other orthogonal with orthogonal velocity vectors. The Hamiltonian system conserves energy. The gradient system dissipates energy. Well, it's actually the opposite of the gradient system that dissipates energy. Actually, with this particular one, energy grows, which sounds crazy, but it's just math here. If we consider the opposite of this, we put minus signs in front of both of those, that would be a system where energy dissipates. And instead of calling this a Hamiltonian function, you'd call its opposite a Lyapunov function, as the term is used. And that is in section 5.4 of the textbook as well. So that's a real quick, big picture summary of some complicated ideas. On the test, if it's in-class portion, it'd probably be a true, false, or multiple choice. If it's take home, it could be longer, though I probably wouldn't make it super hard for this test. Maybe in the final, it could be a longer problem. You'll also read about, and also in the lecture, I talk about tests to decide whether a system is Hamiltonian gradient without thinking about H at all. Just thinking about these right-hand sides, you might wonder, okay, is this a Hamiltonian system? Is this a gradient system or not? There are tests to decide, even if you don't know what H is. By the way, for a gradient system, you don't typically call it H, you typically call it V. Why? I don't know. It's traditional. This function, you call it V, and you call it a potential function because it would represent, in some ways, at least potential energy. Yeah, because in dissipative systems, potential energy dissipates. Gets smaller over time. That's a lot of, again, a lot of information as usual. You want to talk some about linear algebra here. I should also briefly emphasize a few definitions. Like hyperbolic equilibrium point. What's a hyperbolic equilibrium point? The definition is when the Jacobian matrix evaluated at the equilibrium point has non-zero real parts for its eigenvalues. Meaning in the trace-determinant plane, you're not on the t-axis where d is 0, and you're also not on the positive d-axis where you have purely imaginary eigenvalues. That's the definition of a hyperbolic equilibrium point. Why is that important? It's hyperbolic equilibrium points that you can apply linearization to, where linearization is valid. And you can say, for this example, for example, the origin is a saddle point and these two are spiral sources. The official theorem that allows you to do that is called the Hartman-Grobman theorem. I do also talk about trapping regions and stuff. I think for the sake of time, I'm not going to talk about that here in class. As far as the exam goes, it would be just the basic idea. I know the extra reading I gave you, if you did take the time to try to read it, I know it's not easy. Goes into a lot more detail than you would need to know for the exam. I'm just recommending reading that just to get try to see more examples. There are examples in the reading. The writing is difficult because it's really difficult to talk about without making pictures. But I think it would be most useful for us to talk about the main ideas of a linear algebra in the time we have left today. What has been our theme since exam 3 with the linear algebra concept? Our main theme has been diagonalization. And then how is diagonalization related to both systems of differential equations and difference equations? That's been our main theme. Okay, let's emphasize that theme again. We typically think about examples that are either 2 by 2 or at most maybe 3 by 3. But you should know the basic idea of diagonalization in the general case where A is, say, n by n. What are some facts to know? You should know, for example, that if A happens to have n distinct real eigenvalues, it will be diagonalizable. That's one fact. A has n distinct, meaning different, real eigenvalues. That's enough to say A is diagonalizable. We should also remind ourselves what diagonalizable means. I will in a minute here. That's a fundamental fact. That's useful. It's also true if A has n linearly independent eigenvectors, that it'll be diagonalizable. Quick way to say that is A has an eigenvector basis. For Rn. That's also enough to say A is diagonalizable. So these are called sufficient conditions for diagonalizability. If these are true, then the matrix is diagonalizable. However, if these are not true, the matrix still could be diagonalizable. It could be still. If you got a repeated eigenvalue, for example, it could be diagonalizable. You might say it's not likely to be, but it could be. Actually, this one's not just necessary, it's also sufficient. This one's really an orthogonal. But this one is just a sufficient condition, not necessary. There are examples where you've got a repeated eigenvalue that are still diagonalizable. And what does the diagonalization mean and why is it important? The definition of a matrix being diagonalizable, the matrix A is diagonalizable. This is not a theorem. This is saying what diagonalizability means. If there exists an invertible matrix, a P matrix, a change of coordinates matrix, there is an invertible matrix P such that, call it D to be suggestive, D equals P inverse AP is diagonal, or is a diagonal matrix whose only non-zero numbers are on the main diagonal from upper left to lower right. And you can be more specific. If A has n real eigenvectors that are a basis for Rn, you can make them the columns of P, and this will work. And then D will have the numbers in the main diagonal will be the eigenvalues of A. D and A have the same eigenvalues. D and A are similar matrices. They have similar properties, including the same eigenvalues. Different eigenvectors, but the same eigenvalues. Why was this important? Why is diagonalizability important? That's essentially the beautiful generalization, also combined with the fact that diagonalization helps you compute matrix exponential and matrix powers. For the differential equation case, dy dt equals a times y. Go ahead and pretend that's an n-dimensional system. A is an n by n matrix, y is a vector in Rn. And y of 0 equals y sub 0. We know the beautiful generalization says the unique solution of this, which I typically call capital Phi of t, t sub y0 of t, is the matrix exponential e to the ta times y0. That's what the beautiful generalization says, is that's true, that that's your unique solution. How is that related to diagonalization, though? You can show ultimately, through some work, that since, well, D is equal to P inverse AP, that's equivalent to A equals PD P inverse. And because of that, you can show ultimately how to compute the matrix exponential using this fact that e to the TA is really P times e to the TD times P inverse. And that gets multiplied by y0. This is the matrix exponential there for e to the TA is to compute that. That's the way to compute it. If you had to compute it by hand, that's the way to go. We've often relied on technology, but if you had to compute it by hand, that's the way to go. Though if you got bigger than even a 3 by 3, if it was 4 by 4 bigger, even by hand, even knowing this is the way to go, it's still a big pain. For one thing, P inverse would be difficult to find. That's probably the main painful thing about it, is P inverse would be difficult to find. Very time consuming. As far as difference equations go, write your generic difference equation like that. And when I write that again, I'm assuming there is an initial condition, y sub 0 is the initial point. Turns out the solution of this, you could also call this a beautiful generalization, is a to the n power times y0. So now it's not the matrix exponential anymore. It's a to the n power. But diagonalization is still useful. You can still use that here, and through some work, confirm that a to the n power is p times d to the n power times p inverse. That would be the way to compute a to the n power. Can I clarify anything here? This is just, it's stuff that you've been learning about, but it's just very easy to forget. So I'm going through it now with you, trying to spark memories in your mind. It's worth you rethinking about, with examples too, with technology to help you to make the calculations quicker. But to believe you could do, say, calculations, say, for a 2 by 2 case by hand if you had to. This is also related to change of coordinates. I remember it as y equals pu, which is equivalent to saying u equals p inverse y. And ultimately, for the differential equation, it's going to be du dt equals du. And for the difference equation, it'll be un equals du sub n minus 1, and those d's will be diagonal matrices, so these will be simple to solve. The matrix exponential and d to the n are easy to find. But these do correspond to, like, easiest to imagine in the 2 by 2 case, to skewed coordinates. Essentially, like with the differential equation case, your straight line solutions, which are parallel to eigenvectors, become your new axes, your u and v axes. That's what happens when you define this P matrix. And think about this transformation here. You are essentially skewing the coordinate system. What about when A is not diagonalizable? Well, there's two main cases where we thought about where that happened. One, in the 2 by 2 case I talked about the Jordan canonical form. The D matrix here would not be diagonal in that case. It would have a 1 in the upper right corner. But in the 2 by 2 case, it would still be upper triangular. And your eigenvalues, or repeated eigenvalue, would still be on the main diagonal. And since it's upper triangular, it's still relatively easy to compute either CA and d to the n. It turns out. Another case we thought about is what about when A has complex eigenvalues? In the 2 by 2 case, we thought about it. Then you could compute a diagonal matrix if you allowed complex entries, but we're really after real entries. And if you do this kind of thing with the complex case, where P has columns that are the real and the imaginary parts of the eigenvectors, the D does not end up being diagonal, but it does end up having a special nice form, this kind of form. So it's not diagonal, but it's still got a pattern to it. And because this has a pattern, that still makes it relatively easy to work with. Because you can think about this as geometrically as a rotation plus combined with a dilation. These things are in the PowerPoints too. What else have we done in linear algebra since exam 3? Started talking about orthogonality more, dot products, and an introduction to what are called inner products. More about projections and this thing called the Gram-Schmidt process that gives you an orthogonal basis. And orthogonal bases are nice because that's what allows you to compute the projection vectors more easily. When I talk about the projection vector, so I've got W is a subspace of Rn, say. With orthonormal basis is the best one to use, actually. Well, we can use orthogonal basis. With orthogonal basis, call it V1 through VK, say. So this is supposed to be an orthogonal basis of W. W is supposed to be a k-dimensional subspace of Rn. If you don't start with an orthogonal basis, you can make one. That's where the Gram-Schmidt process comes in, is you can make an orthogonal basis. It's an algorithm to construct one. Definitely easiest to do when k is two-dimensional. It's much more painful when k is 3 or bigger. I'm not going to write the Gram-Schmidt process down, but let's just emphasize the main point of all this. Given a vector y in Rn, we want to compute the projection vector of y along W. It's a generalization of projections that we talked about way back in September. Pretend n is 3, so we're talking about R3 here and k is 2. So this is supposed to be a picture of R3 here. And W is a plane through the origin, say, maybe like this. And we found an orthogonal basis for W, two vectors that are parallel to this plane and have a 90-degree angle. This is supposed to be a right angle there. I'm trying to draw it with some perspective. So that's a V1 and V2. And we have this other vector Y, let's say out here, not lying in W. The question is, the useful question to be able to answer is, what is the projection of Y along W? What is its shadow if light rays were coming in perpendicular to W? What kind of shadow would Y cast on W? It's called Y hat. Turns out that Y hat is a useful vector to think about in relation to Y. For one thing, it is the closest vector in W to Y. In terms of if you put both of their bases at the origin, the tips are going to be closest together. And again, once you got an orthogonal basis, the formula for Y hat is simpler with an orthogonal basis. That's why orthogonal bases are useful. And the formula, the general formula is Y hat is Y dot V1 over V1 dot V1 times V1, which is the projection of Y along the line through V1, plus the projection of Y along the line through V2, plus, etc. The last one would be the projection of Y along the line through VK. It's a dot product there. Sorry, these are dots. That's a pretty nice formula to find the closest point in W to Y. Also turns out you should be able to find another vector that's in a subspace called W perp, which consists of all vectors in Rn that are perpendicular to all vectors in W. And if W is a plane to the origin in three-dimensional space, then W perp will be a line to the origin that's perpendicular to that plane. And the vector in W perp that you want to pick is Y minus Y hat. That's in this subspace W perp. What's all this good for? This particular kind of visualization with these particular kinds of vectors in Rn, I can think of applications in statistics as kind of the main application. It can ultimately help you find what are called least squares lines for data. I think on my blog, like about the 5th section, I talk about that a little bit at the very beginning of the article. But also after exam 4, on Friday and next week, we're going to see that this perspective generalizes to these inner product ideas and ultimately to Fourier series, which you may have heard of. Very, very useful in engineering. And not only are Fourier series useful in engineering for, in particular, like signal processing, but Fourier series are also useful for partial differential equations, which come up in the last few lectures as well. What's going to happen after exam 4? Those things I just mentioned will happen. What are the main things you'll need to do for the last, I think it's about 4 lectures or so that you'll need to know for the final? The main thing, calculation-wise, from the textbook, it's chapter 6 about Laplace transforms, which is a very different topic than all this. The other things that I talk about in the lectures are, you might say, harder than Laplace transforms, including partial differential equations, and also more about nonlinear systems, more about the Hartman-Grobman theorem, and linearization. With those subjects, they can be very in-depth, and it's worth trying to understand the depth, but as far as what you're tested on, it's more the basic idea. Okay, so you want to watch the lectures to try to get the main idea with those parts. Because if I put those on the test, I have to give you a ton of information, or I have to give you a one or two problem test, because just the calculations, for example, to solve a partial differential equation just take way too long. Okay, but we are getting into stuff that's still worth learning the basics about, because it will definitely help you. For example, in math methods, you will have to solve partial differential equations in math methods on tests, even maybe with some help or something. I don't know how they do it. Okay. So the goal with that is to set you up for success in later courses. All right, we're writing the exam tomorrow, and if I think of more information to send you, I'll let you know. The CP is up.